Okay, so look, so the 95th quantile for a standard normal probability distribution is equal to, so we want to know where 95% of the area is underneath, so really that's just our inverse normal. Inverse norm 0.95 for a 0, 1, which is our standard normal probability, and 1.644 is the Z value. So what's that, D? Similarly, we just, with a given specific attributes of a 210 normal distribution, those who complete the test in less than 208 minutes, so from negative infinity to 208 for a 210 is 0.788, so D. We often need to use symmetry properties in around here. So if we have a normal distribution with mean 11 and standard deviation of 0.25, the random variable Z has a standard normal distribution, then the probability that X is less than 10.5, well, what's an equivalent Z expression for that? Well, if Z is equal to X minus mu on sigma, the probability that probability that X is less than 10.5, 10.5 minus mu on sigma is the same as -2. So an equivalent expression is the probability that Z is less than -2. It's not there. But from symmetry, we know that the probability that Z is less than -2 is the same as the probability that ZB is greater than 2, and that is there. Okay, so you've just got to shop for the right form of the answer. Children in an amusement park, not distributed with mean 130, standard deviation 2.7. 35% of the children are not allowed to go on the ride. So the bottom 35% can't. So again, the inverse normal, 0.35% of the population for a 132.7 distribution. The bottom level is 128.95. So if I round that up to 129, that means that a minimum of 35% won't be allowed to go. What have we got? X normally distributed, mean 14, standard deviation of 2. Again, we're trying to find equivalent expressions here. So what is the probability of X as being greater than 17 the same as? Well, if X is equal to 17, an equivalent Z expression, or Z value, is 3 on 2. So the probability that X is greater than 17 is the same as the probability that Z is greater than 3 on 2, which is equivalent to Z being less than -3 on 2, because that'll give me the other part of the distribution. So, if we have our distribution there, geez, that's a bad distribution. 3 on 2 is that tail. So less than -3 on 2 is that tail. So Z less than -3 on 2 is also an equivalent expression, which is that one. Humming straight along. Okay, random variable X, normal distributed mean 20, standard deviation of 6. We need to find a comparable interval. That's 2 standard deviations below and 1 standard deviation above. So again, let's draw our curve. So 2 below and 1 above is from 8 to 26. Okay, that's what I'd be looking for, but it's not there. So an equivalent area will be 1 below and 2 above, which is 14 to 32, and that one is there. All right, so again, don't just settle for one that's close to it, shop for the right one. All right. Normally distributed mean 30, standard deviation of 5. For a given number A, the probability that X is greater than A is 0.2. What is A? Well, again, if we want the area, doesn't hurt to do, I'm not doing that, it's embarrassing. All right, let's get a nice distribution, that looks a bit better. We want the probability that being greater than A is 0.2, okay, which means we need the area below being 0.8 for a 35 distribution, which is 34.208, which is 34.212 decimal places. Finally, a little bit different. Orchard, 2,000 apple trees. It is found that 1,735 trees have a height greater than 2.8 metres. If the heights are distributed normally with a mean mu standard deviation 0.2, what is the value of mu? So we know that in actual fact, 17 over the probability that X is greater than 2.8 is 1735 over 2,000. So the probability that X is less than 2.8 is the 1 minus, which is 265 over 2,000, which is 0.1325. So I know that 13.25% of my population is below 2.8. What's an equivalent Z value for that? It's there. An equivalent Z value for 0.1325 is here in my CAS, which is negative 1.1146 standard deviations below the mean. So then if I use my Z equals X minus mu on sigma, I can rearrange to solve for mu equal 2, which in this case will be 2.8, which is the measurement we're dealing with, minus Z times the standard deviation, which comes out to be 3.02. Okay, which is A. Right.